very old.
Okay, so a quick reminder, the homework 4 will be due by the end of this Wednesday. I already gave some hints for homework 4, and if you were not in the class last Monday and Wednesday, you can watch the recorded video. So the hints are given at the end of last Monday's class as well as the beginning of last Wednesday's class. So make sure you check the videos if you need more hints. And you can also come to my office hours this week if you need help. Okay, so today we're going to keep talking about entanglement entropy, which is a very important concept, not only for quantum information, but also for quantum many-body physics. So just sort of a quick review on what we learned in the last lecture. So if we have a full system in a state given by psi AB, and here I'm assuming the full quantum system is divided into two subsystems, A and B. The simplest case will be 2 qubits, and A is 1 qubit, B is the other qubit. So the combined state is called psi AB, so that is a pure state. And the basic idea is you can look at the entanglement between these two subsystems by looking at the entropy of the reduced density matrix rho A or rho B. Right, so we talk about how to get the reduced density matrix. So if you want to get the reduced density matrix for the system A, you do a partial trace over the system B, and then you look at the full system states. In this case, it's going to be rho AB. And because this is a pure state, so it means the pure state's density matrix is just given by the outer product of psi AB, which is Hermitian conjugate. And you can calculate this numerically. We give some examples. And for example, I think the state we talked about in the last class, this psi AB here, is given by 1 over square root of 3. And we have 0, 0 plus 0, 1 and 1, 1. So you all went through an in-class exercise to find out rho A, which is basically the state of the system A. If you can only measure the system A, this is the state you're going to get. It's going to be a mixed state given by basically 1/3 of 2, 1, 1, 1. So this the trace of this adds up to 1. So that's a reduced state. And then the entanglement entropy and similarly, you can find the reduced state for the system B. So you do a partial trace over the system A, and we also did this in class. So this actually is going to be 1, 1. I think it's 1, 1, 1, 2. So it's kind of like the diagonal terms are a bit different. So the entanglement entropy is defined as basically the entropy of either the reduced density matrix A or the reduced density matrix for system B. So these two are mathematically the same, and we're going to show why that's the case. But in terms of a calculation, what you do is you take the negative of trace of rho A times log of rho A. And usually, so this is the matrix log. The only way to do it is actually to diagonalize the row, which is the same as calculating the eigenvalues. So the easier expression is just summing over the pi and the log of pi, where the pi here are eigenvalues of rho A. So the entropy is always a non-negative quantity. This is because all the pi's are between 0 and 1. So the log of that is actually negative, which cancels with the negative sign in the definition of the entropy. And this definition is very similar to the Shannon entropy in classical information theory. So that's a definition of entanglement entropy. And for this particular exercise, we can actually calculate this explicitly. So we can first calculate the eigenvalues of this rho A. So we actually find two eigenvalues. So P1 is equal to 1/2 plus 6 square root of 5 over 6. And P2 is equal to 1/2 minus square root of 5 over 6. So you get two eigenvalues. And these two eigenvalues should always add up to 1 because the trace of the density matrix is always 1. So sum of its eigenvalues should always be 1. So that's a sanity check. And then we can just plug this in for this case. So it's going to be equal to negative of basically P1 log of P1, negative P2 log of P2. So these numbers are not very nice, but you can sort of use your calculator to do it. At the end of the day, it's approximately equal to 0.38. You can do this on the calculator by plugging in those two numbers. So if you compare it to the maximal entangled state, so we also talk about that. So the maximum value of entanglement entropy for 2 qubits is given by log 2, right? So log 2 is about 0.69. So if you compare these two numbers, what you can actually see is for this particular state, we actually have some sort of entanglement between the 2 qubits, but it's not maximal entanglement. So this entanglement entropy in this simple case allows us to quantify how much entanglement we have between those 2 qubits, right? If it's going to be 0, that means the 2 qubits are not entangled, as you will always get, because the reduced density matrix in this case becomes the pure state. But if it's non-zero, it means you have entanglement. But if it's equal to log 2, that means this is the maximal entanglement you can possibly have. So this tells you a very explicit number you can look at, to quantify the amount of entanglement. All right, so that's basically how you calculate entanglement entropy, by hand or using your computer. So you always calculate the reduced density matrix first. We sort of talk about how to do this by hand if you have 2 qubits, and for more qubits you can use some existing software package to do it. And I mentioned the MATLAB code in the last lecture, and in the homework 5, I'll ask you to do that using your favorite software. I think there are Python and Mathematica routines for calculating the partial trace online as well. You can just do a Google search to find them. And then you just calculate the eigenvalues and do that calculation as what I just did. Just sum over the pi times log of pi. So it's relatively straightforward. Of course, this is not a very scalable way because, as we said, we first need to know the full system's state, right? So if you have n qubits, so that itself has 2 to the n coefficient, then calculating the reduced density matrix is going to be exponentially hard as well. Experimentally, if you have a really large system, we sort of mentioned this paper last time, which is actually trying to do this in a scalable way by calculating the trace of rho squared. So the trace of rho squared is also called purity. So it's not exactly the entanglement entropy, but often it behaves very similarly to the entanglement entropy. You can sort of see the kind of similar. So if you calculate trace rho A f squared, it's not exactly the same as trace of rho A times log of rho A, but in a lot of cases the behavior is kind of similar. And you can, the experimental idea is to prepare 2 copies of the system, and you let the first half of the first copy to interfere with the second half of the second copy. And in that case, effectively you are calculating trace rho squared. So there's this nice experiment we mentioned in the last, at the end of the last class. I can show you it again. So we're going to talk a little bit more about this today as well. So this is done in 2015, and again, you can sort of see that there's like 2 identical, systems, and you do some sort of interference. At the end of the day, you measure basically trace rho squared. I didn't have time to show these detailed plots, but here is basically what they're doing. So this is still a kind of a toy experiment because we only have 4 lattice sites. It's trying to calculate the entanglement entropy between 2 subsystems, and there are like different partitions. Let me see if I can find. I think this one is a little bit better. You can see that there's a system A and B. So the first row is like you basically calculate entanglement between the first site and the rest of the 3 sites, so the purple ones, and then you can also do entanglement entropy between the first 2 sites and the last 2 sites. And then you can also do this more interesting partition, like your system A is particle 1 and 3, and the system B is particle 2 and 4. And then you can also look at the reduced density matrix for either the system A or system B, and then calculate in this case, it's the trace rho squared is also called the Renyi entropy S2, but it's similar to entanglement entropy. So you see different curves here, and the first thing you notice is that the blue one, which is this sort of 1 and 3 and 2 and 4, always have the largest entropy, and then the purple one always have the smallest entropy. The green one is kind of in the middle. There's kind of an intuitive understanding of why that's the case. So first, if you look at the purple one, we know that should have the smallest entanglement entropy because the entanglement entropy is actually just bounded by log 2, or just bounded by whatever you have in the first site, right? So it's it's kind of, usually the largest entanglement entropy is obtained by splitting the system into halves, right? Because the theoretical maximum of the entanglement entropy is just the maximum entropy of the n n over 2 qubits, and that's given by n over 2 times log 2. So you definitely want the even split to get the better. Otherwise, it's always going to be the smaller system size that limits the maximum entanglement entropy. So the first choice is definitely the smallest, and comparing the second and the third, both have 2 sites in each subsystem, and the difference is that if you look at the second case, the green case, then there's a general understanding that these entanglement between the particles are kind of like short range. So mostly like the particle 1 is the first particle or the first site is entangled with the second, and the second entangled with the third. It's not exactly that case, but in a lot of physical state, the entanglement is kind of local. It's only between neighboring sites. And then in the green case, in the second row here, you can see when you do this cut in the middle, most of the entanglement entropy is going to come from just the between the site 2 and 3. But if you're doing the last row, so this partition, you will get the entanglement entropy between the first and the second, and also the third and the fourth. So you can see that there's kind of 2 boundaries there when you partition it in this way. And this is the reason why the blue one is having the largest entropy. So this is something we're going to talk later today. It's called the entanglement area law, in the sense that most physical states, entanglement, you can think about it as like mainly between the nearest neighbors on a lattice or in a many-body system. So this is the reason that you're seeing the largest entropy in the blue curve. And the other thing is, so you can see there's a whole curve here, and this horizontal axis here is basically the interaction strength. So this is actually a Bose-Hubbard model. We briefly talked about it when we introduced the non-interacting bosons, and we have some hopping terms, and we also have some interaction terms. This model is not analytically solvable, but the basic idea is you get a phase transition when you tune the interaction strength. So this is the on-site interaction we talked about before. Like if you put 2 bosons on the same side, they're going to repel, they're going to repel each other. So you get a positive energy there. So when you tune this, you are going to get a phase transition from something called a Mott insulator to a superfluid. So that's basically the idea. So the Mott insulator is like every, all the bosons are just on individual sites. So it's kind of like a product state if you think about it that way. So there's no entanglement. Each boson just sit on one of the lattice, and there's no overlap between them. So this is the reason why they have the smallest entropy. So if you look at this side, so that's a Mott insulator. On the other hand, when you get to the superfluid, it's kind of like the wave function is smeared out, so the particles can basically move around. If you look at entanglement between different sites, then you actually get much more entanglement because you kind of get a superposition state of each particle on different sites. So this is the reason why on the superfluid set, side you actually get larger entanglement entropy. And what you can see here is that this entanglement kind of shows like a sharp increase across this. And you can imagine that at some point you can probably see a phase transition if the system size is large enough. This is only 4 sites, so the system size is minimal. You definitely always see like a smooth transition between these 2 phases. But if you have a large system, these you can actually get a pretty sharp curve. So the entanglement entropy itself can actually be used to indicate a phase transition. So when we talk about these quantum phase transition, we typically look at, for example, the magnetization or the correlation between the spins. But you can also use the entanglement entropy between 2 halves of the system. If that actually shows like a non-analytic behavior, a sharp sort of transition, that's also an indication of a quantum phase transition. And the use of entanglement entropy is actually generic in the sense that it can even work for some topological phase transitions where the usual correlation or magnetization would not indicate any phase transition. But entanglement entropy is very powerful in that perspective. You have a question? Oh, no. I know.
I'm kind of curious at how the entanglement entropy compares to like negativity as a metric for entanglement within the system.
I think it's somewhat similar, but negativity is mainly for like I think it's like a 2-qubit system. Yeah, if you have like it's a many-body system, entanglement entropy is usually better.
Okay.
Yeah. So there are some other entanglement when it's just mainly defined for like 2-qubit systems. So this is for an n-qubit system. But it's similar. It's also like a log of a sort of reduced density matrix. Yeah, of course, the main catch of this is there's always some classical noise in the experiment that you can't really scale this measurement up to many particles. So people are still finding ways to do it. But ideally, if you have a perfect quantum simulator or quantum computer, this is the method to go. So later on, when we are talking, in our next topic, we're actually going to talk about a different way to calculate entanglement entropy. If your physical state are represented by something called the matrix product state or tensor network state, then there's a much more efficient way to numerically calculate the entanglement entropy. So you can do that for a system of a few hundred qubits. So you can actually do that. So it's going to be much more efficient than that. So at least numerically, we have more efficient ways to calculate entanglement entropy, and that certainly tells us something about these different quantum phases, because different quantum phases may have different amount of entanglement in their ground states. So that's one of the reasons we're interested in entanglement entropy. But there are more reasons entanglement entropy is important. So we're going to talk about later in this course as well. But before that, I want to talk about something related to this. So the first one is called the Schmidt decomposition. You might have already learned this in your physics 519. If you haven't taken physics 519, this is a good time to learn. So the Schmidt decomposition is a very important technique, and it allows us to show why the entropy of the row A is always equal to the entropy of row B. So we haven't actually shown why that's the case. It's not very intuitive, especially if, for example, your system A is 1 qubit, your system B is like the rest n minus 1 qubit. How could the entropy of these two be exactly the same? Because one is much larger than the other. And it turns out it has to be the same. So the Schmidt decomposition basically says that for any pure state, if you do a partition into two subsystems, so if you have a many-body system, and you partition them into A and B, then you can always do a decomposition in the following way. So it's equal to the sum of m, and you have a square root of lambda m, and then we have basically phi m of A, phi m of B. So the important thing is first, the lambda m's are going to be larger than 0. So these are positive numbers, because you can immediately see that it doesn't make sense if lambda m is negative. You're going to get an imaginary number from the square root. And the other thing is lambda m cannot be 0. Well, technically it can be 0, but when it's 0, then you just don't include that term in the summation. So it doesn't make sense to even write it down if lambda m is 0. And the other thing is these phi's, for both A and B, they are going to be orthonormal to each other. So this is going to be equal to a delta function. And similarly for the phi m b. So phi m a and phi m b are some basis states in the Hilbert space of the system A or the Hilbert space of the system B. So you choose some basis states in the system A and B, and then you can always decompose this into this way. So the important thing is that this decomposition shows that there always exists such choice of basis state in the system A and B. But it doesn't mean that if you just choose an arbitrary basis for your system A and B as these phi's, it's going to be equal to that. So that's not the case. So this is like there exists a basis for this to be the case. So this is not to be confused with the general decomposition. If you have a state of precise AB, you can always decompose it into something, let's call it M and N, and then we have some coefficient, let's just call it CMN, and then we can always use phi, let's use a different symbol just to not confuse you. Let's use phi M of A, chi N of B. So that is always possible. If you choose any basis on the system A and B, I can call it chi M A and chi N of B, then you can always do a decomposition. For example, if you have a 2-qubit state per psi 1, 2, then I can always decompose it into C00, 0, 0, C01, 0, 1, right? C10, 1, 0, and C11, 1, 1. So that is always possible. So you have 4 basis states here, right? So you can always do this decomposition, and you don't need to use this 0, 1 basis. You can use a plus basis for the first qubit, etc. But this is different. For first, you can see that this is a double summation. You have 4 terms for 2 qubit. This is actually a single summation, and this summation is going to be at most, the size of one of the systems. So this is going to be going to the minimum of the dimension for system A or the system B. In terms of the 2-qubit, this means basically any 2-qubit state, you can always decompose it into just 2 components, some phi 1 of A, phi 1 of B, plus square root of lambda 2, phi 2 of A, phi 2 of B. Yeah, so it means that you can always do it with just 2 terms in the expansion, but you have to find these phi's correctly. Yeah, question?
Sorry, I must be forgetting my quantum mechanics notation. What does it mean when there's 2 kets?
Yeah, it's a tensor product. It's a tensor product between the 2. Yeah, it's a tensor product between the 2.
Okay.
Yeah, so we just ignore the tensor product side. Yeah, good question. Question?
So the advantage of the Schmidt one is just that you can get it to 2 terms instead of 4.
Yeah,
like that's what the
yeah.
main
So it's like So you save a lot of terms. It's a square root of the number of terms if you have n qubits.
Right.
Right. This only have n over 2 terms. So it saves a lot more terms, but you have to find the basis correctly. You can't do this in an arbitrary basis, so that's kind of the catch you pay. And the other good thing is it also ensures that the expansion coefficient are always positive. And it turns out that that's an important property we're going to use later. Of course, there are simple ones. For example, we can talk about this very simple entangled state 1 over square root of 2 of 0, 0 plus 1, 1, right? So if you look at that, this actually coincide. These two decomposition coincide. So it basically means you only have two terms, right? So this is 1 over square root of 2. This is 1 over square root of 2, and then the two phi's are just 0, 0, and 1, 1. So that's a trivial example, but you can cook up more complicated examples. I'm not going to go into this in details, but it basically shows that you can always do this. And the reason why this decomposition is more useful than the sort of the standard decomposition which everybody can do, you just write your state in the computational basis. So this one actually allows you to directly get the reduced density matrix as well as the entanglement entropy. To see this, we can actually see what is the reduced state rho A here if you assume this decomposition. And the reason why this is simple is simply because this decomposition allows us to write things down in a much simpler way. So the trace over B of per side AB, if you have this Schmidt decomposition, it's going to directly give you sum over M, lambda M, phi M of A, phi M of A. In some senses, because each term in the phi AB kind of is in the tensor product. So when you are doing the partial trace, then it becomes much easier. It really just gives you the lambda M as the coefficient, which are the probabilities, and then you have this phi A, phi M A, phi M A. So in this way, you can immediately see that these lambda M's are the eigenvalues of rho A. And then you can calculate the entanglement entropy very easily. So the S of rho A is just going to be equal to sum over M, lambda M, negative log of lambda M. Right, so you can calculate this immediately. So if you find the Schmidt decomposition, those coefficients, also called lambda M, will directly give you the entanglement entropy. And the reduced state can also be obtained directly by basically just doing this. Right? And this also tells you a way to do the Schmidt decomposition. So if you do it in the opposite way, what you can do is you first find the reduced density matrix rho A, and then calculate its eigenvalue decomposition. You find its eigenvalues and eigenvectors. So those will directly give you lambda M and phi A's. Right? So that's the other way to do it. Right? So you have a generic state. You want to find the Schmidt decomposition, just first do a reduced density matrix. Calculate its eigenvalue decomposition. And then similarly for rho B, we can do, you can almost guess the answer is going to be pretty much symmetric. So it's going to be sum over M, lambda M of phi MB, phi MB. And again, if you first reduce the reduced density matrix rho B, you can do eigenvalue decomposition to find those eigenvalues and eigenvectors phi B. So the interesting thing is you can see that the rho A and rho B share the same eigenvalue. So they share the same eigenvalue spectrum. And this is exactly the reason why the entropy of rho B is also equal to sum of M, lambda M, log of rho M, log of lambda M. So it's actually equal to the entropy of rho A. So the reason for that is if you take the eigenvalue for rho A, eigenvalue spectrum for rho A and rho B, they're actually exactly the same. So the dimension could be different. What is happening is there's going to be more zeros. If, for example, rho B has a higher dimension than rho A, then they have the same non-zero part of the eigenvalue spectrum. And then the rest of them is just going to be zero. Because for a larger matrix, you have more eigenvalues, right? The number of eigenvalues is always equal to the matrix dimension. But you'll have more zeros, which doesn't, contribute. Okay, so this is the reason why the entanglement entropy are the same between, rho A and rho B. And these lambda M's also have a name. So these lambda M's here, we just call them the eigenvalues of the reduced density matrix. But a better name to call it is called the entanglement spectrum. So as we said that, the reduced density matrix sort of contains information of the entanglement between these two subsystems. And if you look at the eigenvalues of the reduced density matrix, it's like a spectrum, right? It's like a very special spectrum. And that spectrum can also encode some very important information than of that entanglement. And sometimes this entanglement spectrum contains more information than the entanglement entropy. And the reason is very simple, because the entanglement entropy is just one value out of all these lambda M's. And the entanglement spectrum actually has all the information, has all the lambda M's. If you know the entanglement in spectron, you can calculate the entanglement entropy easily, but not the other way. In recent years, there's a lot of people trying to use the entanglement in spectron to characterize a quantum many-body system, and there are even some sort of machine learning approaches. So if you can, look at for the ground state entanglement spectrum, across a phase transition, if you just feed the entanglement spectrum into a neural network, it can actually, tell you where the phase transition is. So there are, work like this in recent years as well. So it's a pretty interesting property to look at. Of course, it's not very experimental friendly because you still need to measure the reduced density matrix, and people haven't found a sort of a scalable way to experimentally obtain the entanglement spectrum. So this is more like, theoretically interesting. Okay, so the next topic is going to be entanglement in mixed state. So far, when we are talking about entanglement entropy, I always say that we're assuming the system is in some pure state rho AB, right? So then you might ask, what if my full system is actually in a mixed state, which could be true, right? If you have a quantum computer or quantum simulator, it might be that the whole system is not in a pure state because you talk to the environment, there's some noise on the system. So the short answer is that you can't use entanglement entropy for a mixed state. It just doesn't make sense. So entanglement entropy does not measure or quantify entanglement in a mixed state, at least in general. Because you could argue that if you have a mixed state very close to a pure state, then apparently entanglement entropy is still somewhat useful. But we're talking about, in the general case, entanglement entropy does not quantify entanglement in a mixed state. So we can look at a very simple example. So let's just say we have 2 qubits, and then the row AB here is just going to be the identity matrix over 4. So we get a 4 by 4 density matrix, which is just equal to a quarter on the diagonal and 0 everywhere else. Right? We can calculate the entanglement entropy for this state. So the first thing we do is to calculate the reduced density matrix for the subsystem. And I'm not sure if everybody still remembers how we do this by hand. So it's actually relatively simple because it's just for the first qubit, we're just going to trace over these 4 submatrices. So we have 4 submatrices here. The ones that are not written are just 0. Right, so we have 4 submatrices. We look at the trace of each one. So the first one gives me 1/2. The second one is all 0, so it's 0, 0, and 1/2. Right, just adding those 4 diagonals. And then it's easy to see that the entropy for this is just going to be log 2. Right, so yeah, it's actually an identity matrix. So the entropy is log 2. And then we also learned that for 2 qubits, the maximal entanglement entropy is log 2. So this seems to indicate that this state has maximal entanglement, if you still believe entanglement entropy quantifies the amount of entanglement for this mixed state. But this is apparently wrong, because this row AB is in a state given by identity matrix. And an identity matrix, that basically means the state is completely mixed. It should not contain any entanglement. So one of the ways to think about this, if you look at this thing, suppose I use a computational basis, this state actually means I have exactly a probability of a quarter to be in the state 0, 0, 0, 1, or 1, 0, and 1, 1. And there's absolutely no entanglement in such state. It just means with 1/4 probability, the system is in either one of the 4 product states. Right? So the 2 qubits, they're not entangled. So it's a classical mixture of these 4 product states. So there's no entanglement. So this means entanglement entropy is actually not the correct way to quantify the amount of entanglement in such a mixed state. Okay. Any questions? If not, I'm going to ask you a question here. So let's do okay, Sean, you have a question?
So this is not very useful on NISC hardware, is that what this is implying?
It's not that. You're right that all the NISC, quantum devices have mixed state in general. So that means entanglement entropy is somewhat not a good measure. But you can also say that as long as you are kind of close to your pure state, entanglement entropy may still be useful. This is just say conceptually, you should be very cautious of using entanglement entropy for quantifying entanglement in a mixed state, because it should only work when the state is barely mixed, right? So that's just something to keep in mind. Yeah, good one. Okay, so now question. So let's make a more complicated state. So instead of using this is kind of like a trivial state. I want to ask you for the state rho AB, which is given by this: 1/2, 0, 0, 1/2, and 0 everywhere else. So I want you to calculate the entanglement entropy for this system. So S rho A, same as this. So you can repeat the calculation here. I'll give you a few choices. The first answer is the entanglement entropy is 0. The second is log 2. Third is something else. Third is just, the last one is I don't know. Should be relatively simple to figure out this. And you can use your clicker to answer the question.
In terms of, because it's a product, right? 0 times log 0.
If you don't know the answer, calculate the reduced density matrix first. When, we know the trick is just to partition this into 4 blocks, 2 by 2 blocks, and calculate the trace of each one of them. Should be relatively simple. Okay, I think most of you finished. All right, it looks like most of you get the correct answer, which is B, log 2. So it's basically pretty much the same as the example I just showed, right? You calculate the rho A, which is actually also given by 1/2, 1/2. And the reason for that is, again, you just sum over these two is 1/2, these two is 1/2, these two is 0, and these two is 0. So you just do the trace of those 4 blocks, and it still give you the same rho A. Okay, so this state, again, seems to indicate that the entanglement entropy is maximized. But because this is a mixed state, it doesn't mean anything. And this state is, again, not physically entangled because it means there's a probability 1/2 to find the system in the state 0, 0 and in the state 1, 1, right? And neither is entangled.
Would the answer be else?
No, the answer is log 2. The answer is this. Yeah, because
We just said it's a mixed state, so it can't.
No, but that's why the measure is not useful.
yeah, the measure is not useful, but the entanglement entropy is still defined. The quantity is still there. It's not useful, right? So this is just to, it's an exercise for you to calculate. Question, Connor. It's not entangled. Yeah, there's no entanglement in this. Yeah, in this state.
The fact that the entanglement entropy is non-zero does imply that the system is entangled with its environment in some way, right? Or it might imply that.
Yeah, that we don't know because here we are just assuming we don't know anything about the environment. This is just our system. I'm really just asking the question whether A is entangled with B. That's it. Yeah. Again.
I guess I'm confused why that's not entangled.
Yeah, why that's not entangled? Because it's a state that half of the time when you measure it's in the 0, 0, and half of the time it's in 1, 1. But it's not a coherent superposition of 0, 0 plus 1, 1. So this is a very good question. So for example, the opposite example of this state would be 1 over square root of 2 of 0, 0 plus 1, 1, right? So that will be a true entangled state because it's not what that state is. And you can write the density matrix. This is an excellent point. So if you write the density matrix of this, it's actually pretty easy to see that you get 4 1/2s in the corner and 0 everywhere else. So it's like very close to the state we just wrote down, but a little bit different. You see this off diagonal, right? So that's the tricky part. This is a pure state and that's a mixed state. Yeah, question.
So if you take the density matrix of a pure state, you're
Yeah.
going to get some kind of maybe
Off
something like
diagonals.
that, but
Yeah.
the density matrix can be any like arbitrary ensemble.
Yeah, it could be any arbitrary one. As long as it's trace 1, it's semi-positive. Definitely it's fine. And that rho AB I just wrote is perfectly fine. So it's a perfectly fine density matrix, and it does have a physical meaning. It's 1/2 in 0, 0, 1/2 in 1, 1. But it's a classical mixture, right? We're going to talk about what that corresponds to a classical case. Actually, I can explain what that state is in a classical example. So think about 2 coins. the heads correspond to 0 and the tails correspond to 1. So this will be two coins entangled. It's not a classical object. But the state I just wrote there as an exercise, so that one is actually just two correlated coins. You can think about just two coins stick by glue, right? And then they're always either 0 or 1. And if you do a flip of that coin, and that two coins together, they're going to be either 1/2 chance you get both of them, heads up, or both of them, heads down, right? So it's basically a classical mixture of that. And you can not say that these two coins are entangled, right? So, this is basically a classical system.
I'm still confused then why the answer is log 2, because that's telling you it's entangled when it's not. So it's
Oh,
giving you
yeah.
this
So the thing is that the entanglement entropy just does not quantify the amount of entanglement if the state is mixed, right? So the entanglement entropy just don't talk about entanglement anymore. It's mathematical, you can still write it down, but it doesn't quantify the entanglement. So that's the thing. So it's log 2, but it doesn't say anything about how much entanglement you have. So that link is broken, right? Yeah. So you still call it entanglement entropy, but technically, so the other way to say it is entanglement entropy is only well defined if the system is in a pure state. If it's a mixed state, entanglement entropy is a very bad concept. Right? It doesn't even tell you anything about entanglement. So that's just to be clear, right? So as Sean asked earlier, if you want to use entanglement entropy, you should make sure that the state is at least very close to a pure state to make any sense. Because in this case, entanglement entropy doesn't make any sense, right? Okay, so now the question is, for mixed state, entanglement entropy doesn't work, but is there a different way to quantify how much entanglement you have? So there are indeed. First, there's this quantity called mutual information. So this one is also defined in a way that we can calculate directly. So it's typically denoted by the letter I. So I stands for the mutual information here, and it's between two subsystems A and B. So this one is defined as S of row A plus S of row B minus S of row AB. So it's the entropy of the subsystem A plus the entropy of the subsystem B minus the entropy of the total system. And you can see that if you actually have a pure state, this one reduces to entanglement entropy largely because for pure state, row AB, so the entropy of row AB is going to be 0, right? Because the pure state has 0 entropy. So this one is gone. And then S row A is equal to S row B, as we just said, according to the Schmidt decomposition. So this mutual information is really just 2 times of the entanglement entropy. So for pure state, so this basically just reduces to 2 times of S row A. So it's double the entanglement entropy. But for mixed state, of course, it can be different. And to see how it is different, we can look at this old example of row AB equals to identity matrix over 4. And in this case, row A is going to be just 1/2, 0, 0, 1/2. Row B is the same, it's symmetric. So we can calculate the mutual information here. So S of row A is S of this, so that entropy of this is just given by log 2, right? Because this is a identity matrix. And then similarly for S of row B is also log 2. And then we can also calculate the S of the whole row AB because, again, it's an identity matrix. So it's basically given by 2 times log 2, right? A complete mixture state always have the entropy given by n times log 2, right? Now do the math here. And this perfectly cancel. So this actually shows that the mutual information between these two qubits is exactly 0. So this is definitely more useful than the entanglement entropy because the entanglement entropy tells you that this complete mixture state actually has a log 2 maximized entanglement entropy, but for the mutual information it actually shows you 0. So the mutual information in this case tells you that these two qubits basically are not, at least there's no entanglement. So, a more accurate the mutual information quantifies the amount of correlation.
Can we mean quantum correlation specifically?
I'm going to talk about that later. Yeah, quantifies the amount of correlations between A and B. And for the complete mixture state, because it contains no information, there should be no correlation between the first qubit and the second qubit. Okay, so I'm going to explain whether that correlation is classical or quantum just in a little bit. But I want to first let you do a small exercise. So we just introduced this mutual information, and I want you to calculate the mutual information for this state we just calculated. And still, I give you, you know, these answers. So you can see which one it should be.
By the way, just notationally, is that a colon separating A and B?
Yeah, it's a column, yeah. Separating A and B. So this shouldn't be hard. So you just need to calculate the entropy of row A, row B, and row AB. And row A, row B for that one is actually, we just already figured it out. So both row A and row B for this is just equal to the identity matrix. And then the basic thing is you want to calculate the S of row AB. And if you forget how to calculate the entropy, it's the sum of its eigenvalues times the log of the eigenvalues. And you only sum over the non-zero probabilities. So it shouldn't be hard to figure out. Okay, you can use your clicker to make a choice. So same 4 answers. So in this case, whether the mutual information is also 0 or something else. Okay, if you know the answer, make sure you use your clicker to answer it. Okay. All right, so this is interesting. We got a lot of you choosing A, and then some choosing B. Yeah, so it's not that clear what the answer is. So the A is actually not the correct answer. In this case, it's actually not 0. The correct answer is B. So log 2 should be the correct answer. So let me walk you through this. So again, the definition is given by this expression, and it just said row A and row B, they're both identity matrix, same as the last problem. So this is just going to be log 2, and that's also going to be log 2. And then the S row AB, so this one is a bit tricky. So you're going to look at the big matrix there, and we're just looking at its eigenvalues because it's already diagonal. So the 2 eigenvalues are just given by 1/2 and 1/2. The other 2 are given by 0. We don't count the 0 ones because they don't contribute to entropy. So we're just going to sum over this. So you actually get 1/2 of log, so there's going to be a negative sign there, 1/2 of log 1/2 plus 1/2 of log 1/2. And then if you do the calculation again, it just becomes log 2. There's going to be a negative sign in front. So it's again log 2. So the entropy of the whole matrix is actually log 2. So this is going to be log 2. So you get log 2 plus log 2 minus log 2. So the correct answer is actually log 2. Right. Yeah, question, Bora?
Does that mean our mutual information score isn't as great as we thought it was? Because for your one mixed state it has like 0, but for another mixed state it has a non-zero quantity.
Yes. So the mutual information, of course, can be 0, but it can also be, I think the largest one you can get, let's see. So the largest one you can get is actually basically 2 times entanglement entropy. So in this case, the largest one you can get is 2 times log 2, right? So for this particular 2-qubit case, the mutual information can be anything between 0 and 2 times log 2. And the example we just calculated is somewhere in between. So it's just log 2, right? And as we just said, the mutual information quantifies the amount of correlations in the system. As long as it's non-zero, it means that the 2 systems are correlated, right? The 2 subsystems are correlated. And we just explained that this state in the question is actually corresponding to a classical mixture of 0, 0, and 1, 1. So that does mean that the 2 qubits are correlated, because you can think about it as 2 coins stick together. So there's some correlation here. which is correctly reflected by the mutual information. But the problem of the mutual information is that it does not distinguish classical correlation from quantum correlation, because in this case, the two qubits are only classically correlated, there's no entanglement. So having a non-zero mutual information does not tell you that the two qubits are actually entangled. It only tells you that the two qubits are correlated. They're not independent of each other. The measurement of one depending on the measurement result of the other. So that's what it tells you. And you can see that here, it already tells you that it's kind of very hard to distinguish entanglement from correlation in the mixed state. So for a pure state, if you have correlation between the two qubits, it definitely means that the two qubits are entangled, right? So for pure state, entanglement is pretty much equal to correlation. And you don't even need to say whether it's quantum correlation or classical correlation. As long as it's a pure state, correlation is just quantum correlation. And the reason is very simple. We see from the mutual information, if it's a pure state, this is basically just 2 times the entanglement entropy. And if one is larger than 0, the other one has to be larger than 0 as well, right? But it's only in the mixed state we actually have this example where we have a non-entangled state, but we have a state with positive mutual information. So one interesting thing is, if you're looking at a maximal entangled state for calculate the mutual information, it does give you larger correlations. It's 2 times log 2. So in some sense, you can say that if you have quantum entanglement, it contributes to mutual information about twice as much as a classical correlation. And quantum entanglement, you can also call it quantum correlation. It's kind of similar. So the quantum correlations does way more than the classical correlation, but it's really hard to distinguish whether you actually have classical or quantum ones. If you don't know, if the correlation is not maximized, it's very hard to detect that. For 2 qubits, you can still develop ways to know whether a mixed state is actually entangled or not. So it's not going to be what we're going to cover. There's something called, for example, negativity, and there's also another thing is called, concurrence. So there are, sort of more complicated, quantities depending on the sort of the density matrix, reduced density matrix of rho A and rho B, that you can distinguish between entanglement and correlation. We're not going to talk about this, but there do exist measures of that. But if you have a many-body system, like more than 2 qubits, then it's extremely hard problem. I don't think there's good answers to this even nowadays. So if you have a many-qubit system and it's in the mixed state, how do you quantify the amount of entanglement in the system? That's a very hard problem, and it's partly just because we cannot distinguish quantum entanglement from classical correlations, just like in this simple example. So I can show you one paper which is kind of very interesting. It shows kind of the this challenge. So this is a paper done with hundreds of trapped ions, and it's trying to generate entangled state between these ions. So this is a science paper, I think a few years back. Again, it's trying to do some sort of transverse field Ising model, as you can see from this Hamiltonian. And what it's trying to do is to first put all the spins, all the qubits in the 0 state, and then evolve under this Hamiltonian. So theoretically, you can show that if the system is pure, if you evolve it for some time, then all the qubits are going to get entangled. And then you should basically show that all the qubits are entangled. But unfortunately, experimentally, we always have noise, right? And once you have the noise, and the system becomes a mixed state, so do you even know the system is still entangled? You can measure the correlations, you can measure the mutual information. Those do show that there are some correlations. But how do you know that those are just not a classical mixture, like a equal superposition of 0, 0, and 1, 1? That's very hard. And one way to think about it is if you start with just 2 qubit at maximal entangled state, the noise can decohere the system, and then the system is just going to go to the state I wrote there, that rho AB. Right? So a maximal entangled state, once it decoheres, so this state, once decoherence happens, is going to take you to that. So this is a challenge. You have to be able to know whether the system decoheres or not. And that is apparently very hard to know. And in this paper, they have about 200, basically spins that, that are evolving under this, Hamiltonian, and that should be entangled, ideally. And they want to basically show how much true entanglement you can prove in this mixed state. They clearly know that the system in the mixed state, and they have to develop something much more complicated. I'm not going to go through the details, but it's actually something called the Fisher information. So you can use the Fisher information to bound the amount of entanglement in your system. So you can show that how many particles are actually entangled, and the result is pretty shocking. So I can show you. I think there's something written there. I can't find it. Yeah. So this is Fisher information is basically larger than 2.1. So this F over n, if that is larger than 2.1, it shows that you can only prove that two particles are entangled. So if this F over n is larger than m, then you can show that m particles entangled. For example, if it's larger than 200, you can show 200 particles are entangled. But unfortunately, it's only larger than 2.1. So that means even though they have 200 spins, doing this quantum evolution, they can only prove that at least two of them are entangled. So of course, this is only a lower bound, but this is the thing that you can prove that you have this much entanglement in the system. And unfortunately, they can only prove, only two particles are genuinely entangled. The other ones might just have classical correlation. So this just shows you how hard it is. And there are similar examples like this. There are people doing cold addons. They have like 1 million addons, and they try to do some entanglement operation. At the end of the day, they can only show that about 1,000 of them are entangled. I think the record is kind of like this. You can only show like 100 or 1,000 of your particles are genuinely entangled. It's very hard to show even 10% of your qubits are entangled. And this is kind of a pretty important problem in quantum computing. I think D-Wave is kind of also trying to do this type of experiment because they have a lot of qubits. They already have 1,000 qubits. But after you evolve the system for a while, how do you even know that there's genuine quantum correlations, not just these classical correlations, which comes from entanglement, but the decoherent version, right? That's kind of like the more classical mundane version. And they also couldn't certify that they really have many qubits entangled, right? Even with 1,000 qubit, maybe they can show a few of them are entangled, but showing even 10% is hard. And one of the reasons, of course, is because of the decoherence, right? There's always noise there, and that absolutely make some of the quantum correlations go to classical. But the other thing is we just don't know the way to analytically calculate this amount of entanglement. You can only derive some bounds, and usually these bounds are just terribly loose. Of course, if you know the actual full density matrix, you can always calculate it brute force. But unfortunately, that is not even possible numerically, just because the density matrix contains too many numbers. So this is a hard problem. I just want to point out that, and keep in mind that if you are talking about how to quantify entanglement in a mixed state, that is a very challenging problem. Yeah, so that's the bottom line. Any questions? Of course, this question is kind of important because we all know that if you only have classical correlation, then you shouldn't get a speed up by doing that calculation, right? So entanglement is kind of a necessity for quantum speed up. There's one small sort of loophole to this argument. So somebody actually find that you don't necessarily need quantum entanglement to show a speed up. So there's something called quantum discord. So for those interested, you can search this on Google. So it's kind of like a tier. So entanglement, of course, is the best quantum resource. If you have entanglement, that means it's definitely not quantum, right? So the classical system cannot have entanglement. But there's also something in between of a classical state and an entangled state. And that thing is called a quantum discord. So sometimes this is also called a non-classical, non-entangled state. So it's kind of weird, right? It's not classical, but it's also not entangled. And this is definitely impossible for a pure state. For a pure state, it's either classical, which we know as a product state, or it's entangled, right? For pure state, everything is simple. Calculating the amount of entanglement is all simple. We just learned the entanglement entropy. For mixed state, unfortunately, it's like a whole monster. And you can even find these sort of really bizarre states, which you can show that there's no entanglement. But on the other hand, it's also not a classical state. You can't model it as a correlated coins. So there are states like this, and people have shown that this type of state can also be used to speed up computing. You can actually get at least some constant speed up compared to classical algorithms. So this is one of the reasons that D-Wave is arguing, even though they don't think their system, at least most people don't think their system is genuinely quantum. There's a lot of classical correlations there. They may still be able to get some speed up, but this is like kind of like a marginal topic because people, most people in quantum computing community still only build quantum computers out of entanglement, right? So we are assuming that we have entanglement in the system in order to get quantum speed up. So this is kind of like a gray area. All right. So that's about entanglement. This is a very important concept, and we talk about mixed state and pure state, how to quantify them in a many-body system. Okay, so now we're going to come back to this topic we talked about for the entanglement area law. So this is a pretty new concept. I think it's only basically discovered less than 20 years ago, but it's a very important concept now. Everybody knows it. It basically shows that for most physical states, the amount of entanglement is actually not that much. So that's kind of the the short way to say it. You don't expect every particle to be entangled with every other particle. You actually only expect the particles to entangle with its neighbors. So I can show you some pictures here to give you a better understanding. I guess you can find a lot of pictures by just typing this on Google. So here's a good one. So you can see that there's a lot of particles here. And the line here basically is like a schematic way to represent that these two particles are entangled. So if I draw a line here, it roughly means these two particles are entangled. And clearly, this is kind of like a graph of these qubits, which is mainly consist of nearest neighbor entanglement, right? Each qubit is only, lined up with some neighboring ones. So here's the thing. So if you actually choose a subsystem, so for example here, this shady region in blue is going to be the subsystem we're looking at, then you can see that the amount of entanglement it has with the rest of the system actually only scales as basically the size of the boundary, right? So maybe this one is a better one in that sense. It's kind of similar, but you can see that this subsystem A, the amount of entanglement it has with the rest of the system is kind of basically only the number of lines you are cutting for that boundary. Right? The boundary is cutting through a bunch of lines there, and that's basically it. Right? It's not going to actually scale with the number of qubits or number of particles inside this region A. So this is a basic idea. So most physical states, the entanglement is kind of only between the neighboring sites, the physically neighboring sites, and then the entanglement entropy is also going to only scale linearly with the number of sites at the boundary. Right? So you basically just count the number of particles at the boundary of this subsystem, and that gives you the scaling of the entanglement entropy. The reason why it's called area law is usually we're thinking about this in 3 dimensions. If you have a 3-dimensional system, then the entanglement entropy is basically proportional to the area of the subsurface, right? Of the surface that separate your subsystem from the other. Right? For a 3-dimensional system, the subsystem, the boundary is actually 2D. So we're talking about the area of this. But if you have a 2-dimensional system, then it's actually the perimeter of the boundary. And if you have a 1-dimensional system, it's really just 2 points, right? So the subsystem is just defined by 2 points. So that's basically an intuitive way to understand area law. So I can write this down. So it basically says that the entanglement entropy for most physical state, and we'll define what physical state actually means just a bit later. But for now, you can just say that most of the states, we see. Entanglement entropy scales, or maybe just proportional, is to the size of the boundary between 2 subsystems. So only the boundary size matters. So how big is the actual size actually does not matter. Question, Connor?
I guess I'm just a little confused about what even defines the boundary between subsystems. What makes how you decide what a subsystem is.
Oh, the boundary. For example, here's a picture I drew in my lecture notes. So we have a very nice square lattice, right? So then we can call this system X, and then the boundary here is basically just given by that, right? The size of the boundary.
How did you decide that that was a subsystem?
Oh, you have like enclosed. So basically, the boundary is going to be a closed it's going to be a closed region, right? So it's a closed region, right? So and that is your subsystem, and the rest of them is the other. Right? It's just any closed region, any closed region in space. That makes a subsystem. And then there's always a boundary it makes with the rest of the system. And you're just counting the size of the boundary, right? For 1D, it's just 2 points. 2D is a perimeter. 3D is a surface. Question, Paul?
The first graphic you showed had a donut inside.
It doesn't really matter. Yeah, you're also going to count that linear, right? Yeah, so it's like the perimeter of the outer one and the inner one. Yeah, so the perimeters of those two added.
Can you make multiple donuts?
Yeah, you can if you want. Yeah, so you're always going to count the total number of boundary size. Yeah, question, Sean.
So if you said like most entanglement is nearest neighbor,
Yeah.
like what's happening at the boundary that like wouldn't some of that entanglement like go outside of the subsystem?
If you have periodic boundary condition, maybe that's okay. But normally, physical system at open boundary, it just means this qubit is not talking to anybody else. It's just talking to this. Yeah. Yeah, yeah, of course. For example, you can also just cut the system into halves, and this is going to be the boundary. And these boundaries don't actually make any sense. It's really the boundary makes with the other system. So you only count the boundary makes with the other half. The boundary makes with like the environment, that doesn't count. Right? So you only count the boundary between the two subsystems. Right? Of course, this is kind of mostly just a scaling. Right? If you have like a real boundary and if you calculate exactly the entanglement entropy, you have to do the calculation. But this is basically saying that the scaling is making sense. If you have a large enough system, then mostly it's just going to scale with the boundary size instead of the volume of the actual system. Okay, so now I'm going to sort of define what most physical states actually mean. So there are a couple of categories we can talk about. So first one is going to be ground state. Oh, sorry. So the first big classes of physical states are ground states of gapped local Hamiltonian. So let me define what gapped and local mean. So the gap basically means there's an energy gap between the ground state. If you have degenerate ground state, that also counts. So they all just call the ground states. But there's a gap, energy gap between the ground states and the first excited state. So that energy gap does not go to zero as the system size goes to infinity. So that's what we call a gapped Hamiltonian. And examples of this is, for example, we talk about the transverse field Ising model. So it's going to be a gap Hamiltonian in both the ferromagnetic state and the paramagnetic state. So it's only not gapped or gapless at the critical point. So most Hamiltonians are like this. Unless you're at the quantum phase transition point, most Hamiltonians are going to have an energy gap. So the gap Hamiltonians are pretty common. The other one, the local one, basically means that the interactions are short-ranged. So like nearest neighbor interaction, or maybe going to the next nearest neighbor. But it's not going to be like one particle interacting with another particle at the end of the other end of the system.
So that locality is part of why.
Yeah. So you're right. So yeah, this is a very good point, right? So the reason why we see that the entanglement is also kind of local, first is because the interactions are local, which kind of directly translate. The other is actually because there's an energy gap. So later we're going to talk about why the energy gap is actually important. It's actually something related to adiabatic quantum computing. So these two conditions are needed. So both has to be gapped and local in order for ground states to obey the entanglement area law. In this case, you can pretty much think about that the ground state only contains local entanglement. Right? And of course, you can violate this, for example, by having long-range interactions, which are sort of more common nowadays because of these quantum simulation and quantum computing platforms, but still less common than short-range local Hamiltonians. And if you don't have the gap, like at the critical point, actually area law is supposed to break. The entanglement area law is supposed to break. And we'll talk about that later. So this big class actually already consists of most interesting state. This even includes topologically ordered state. Yeah, we talk about sort of the topologically ordered state, before, so they're very important, not only for the condensed matter point of view, but also for, quantum computing. And a lot of these, quantum error correction codes are made of topologically ordered state. And it's actually important that the topologically ordered state has to be ground state of gap local Hamiltonian. So first, the energy gap makes sure that this topological order cannot be easily killed. So if you have energy gap, that means it takes a certain amount of energy to excite the system to some different state, some excited state, right? If there's no energy gap, that means a tiny bit of perturbation is going to take you to the excited state, which is not good. And apparently, if you want to use topologically protected qubit, you do want there's an energy gap that prevent the system from destroying your information, right? And the energy gap, the larger the better, right? It's kind of like a barrier for you to get error. And local is also important. That means interactions are local. Then we know that the topology, all this topological order, is making sure that this whole thing is robust to local perturbations. If your interactions are non-local, then any perturbations could also travel non-locally through your system and destroy this topological order. So topological order is only robust under local perturbations, which is the reason why we also have to assume the Hamiltonian has local interactions. Okay, so in the next topic we're going to cover, we're also going to talk about these matrix product states and tensor network states, which are its two-dimensional generalization. So especially the tensor network state can actually represent most topologically ordered states. So these also belongs to something like this. So they also satisfy entanglement area law, and they can represent ground states of gap local Hamiltonian. Okay, so this is probably the largest class of states satisfying entanglement area law. So there are some other ones which are less, perhaps less sort of related to quantum information. For example, all eigenstates of many-body localized Hamiltonian. So this is a pretty important concept, but I'm not going to explain what a many-body localized system exactly mean. But basically, it tells you that this is like any system that has a lot of disorder in it. Then all the eigenstates should satisfy entanglement area law. So this is pretty common in material science. If you have like a really dirty material, like this material has a lot of defects, a lot of strain, a lot of disorder, in this case, then most of the eigenstates of the electrons are going to be called localized, and they basically satisfy entanglement area law. So there's not much entanglement in those systems as well. So you have strong disorder in the system. For example, you apply magnetic field, but each side has a different magnetic field. A random magnetic field, that's called a disordered system. For these systems, we believe all the eigenstates, not just the ground state, should satisfy the entanglement area law. Question, Cody?
Since like trapped ion quantum computers can have non-local interactions, do they not satisfy the entanglement area law, or is it like a small enough space that there's...
So yeah, that's a good question. It kind of depends on how long range the entanglement is. Yeah, let me actually... So I myself is actually an expert in this area. So actually I have a paper on this. See if I can find it. So I actually have a paper a couple of years ago for how to, whether long-range interacting systems satisfy entanglement area law. So this result basically shows that, if the interactions decay as a power law and with some coefficient alpha, if alpha is larger than some critical value tied to the dimension of the system, then the area law still survives, which does make sense, right? If it decays fast enough, it shouldn't be very different from nearest neighbor interactions. But if it's smaller than that, it shouldn't be. And one thing I want to highlight is I got a pretty famous author here, Fernando Brandao. So he's actually the head of the Amazon Quantum Computing. And his main contribution to this paper is to just tell me how to do this. So he basically said that you should look at quasi-adiabatic continuation. That's it. And then I look at that and it worked out. That's it. And I asked him to send me any feedback to my paper, and he didn't respond. And the only time he responds is the paper get accepted. And he said, "Congratulations." And it's actually the paper I got accepted the first round, so it's pretty amazing. I submitted, and then both referees like it, and it's immediately accepted. So. Okay, anyway. So that's a good question. So the other thing I want to talk about, there's another very important class of states which satisfy area law, which is directly related to quantum computing. So it's like all states generated, assuming from a product state, by a finite depth local quantum circuit and this is actually equivalent to a finite time evolution of a local Hamiltonian. So we just explained a local Hamiltonian is a Hamiltonian where the interactions are short range, like nearest neighbor or next nearest neighbor. It's not long range. And a local quantum circuit is very similar. So it's a quantum circuit where you can only perform 2 qubit gates for 2 qubits which are physically, close to each other. Like you can do like, a gate between 1 and 2 and 2 and 3, that's fine. But you can't do like a gate between the qubit 1 and qubit 100, right? So that's not a local gate. So that's what a local quantum circuit means. Finite depth basically means you can only apply gates. You can do parallel gates, but they have to be a finite layer of them. So it's the finite circuit depth. And finite time evolution, that's pretty easy to understand. So you evolve under a local Hamiltonian for a finite time. So all those are going to generate states which satisfy entanglement error law. Of course, this is assuming you start with a product state. And this is actually not hard to understand. So suppose you start from a product state, and if you can only apply these local quantum gates, like these 2 qubit entanglement gates, for a finite number of layers, then pretty much the entanglement is going to be also local between the sides, right? You can only create entanglement between the neighboring qubits. Right? If you want to entangle one qubit with a qubit very far away, then you need a lot of sequential entanglement gates to get from one to the other. And that will not be a finite depth quantum circuit. And similarly for finite time evolution. So these two are pretty much equivalent because you can think about a quantum circuit as being implemented by a time-dependent Hamiltonian. You basically just evolve from that. Okay, so I'm running out of time. I'm going to stop here. So in the next class, we're going to talk about states that do not satisfy error law. There are also some good examples, and we'll go from there. All right, have a good one. See you on Wednesday.